In the last video, we discussed about the Coastal-Lewis approach to chemical bonding, and we also discussed the limitations of octet rule. Now, the next theory related to chemical bonding is VSEPR theory. But before we come to the study of VSEPR theory, we have to study certain terms related to chemical bond. So, we are going to study about those bond parameters. So, this video is about the different terms used to describe a chemical bond, which are called bond parameters. So, bond parameters. The first bond parameter is bond length. Bond length. What do you mean by bond length? From the name itself, you know it's the length of the bond. But when you are asked to write as a definition, bond length means it is the distance between the center of nuclei of two bonded atoms in a molecule. So, if we have two bonded atoms in a molecule, how can you show the bond length? It is the distance between the center of nuclei. D. This is the bond length. Okay, distance between the center of nuclei of two bonded atoms in a molecule is called bond length. And bond length is usually expressed in terms of picometer or angstrom. We know that 1 picometer is equal to 10 raised to minus 12 meter and 1 angstrom is equal to 10 raised to minus 10 meter. So, bond length is expressed in picometer or meter because it is the distance. Okay, so it will have the unit of distance. Now, for ionic compound means it has a cation and anion. Bond length will be the sum of their ionic radii. That means for ionic compounds, the bond length D will be the sum of their ionic radii. What do you mean by ionic radii? Ionic radii is the distance between the cation and anion in an ionic compound. Okay, now for covalent compounds, the bond length will be the sum of covalent radii. So, for covalent compounds, the bond length will be the sum of Ra plus Rb, covalent radii. R, A and B represents atom A and atom B, covalent radius. Now, what do you mean by Ra is the covalent radius of atom A, Rb is the covalent radius of atom B. What do you mean by covalent radius? Covalent radius is half the distance between two similar atoms joined by a covalent bond. For example, you know chlorine molecule is formed by a covalent bond. So, if we have two chlorine atoms, means this is a chlorine molecule, the bond length means the distance between the center of nuclei of two bonded atoms. This is a chlorine molecule. So, if this distance is 198 picometer, then, so this is the bond length of chlorine molecule of Cl2. Chlorine molecule is 198 picometer. What will be the covalent radius of chlorine? Covalent radius will be half of bond length, that is 198 by 2, which is equal to 99 picometer. So, covalent radius, how will you show the covalent radius here? Covalent radius will be, the distance will be from here, sent nuclei to this, and this also from here to this. So, this is 99 picometer. This is also 99 picometer. Okay, so total will be the bond length, that is 198 picometer. So, covalent radius means it is half the distance between the two similar atoms joined by a covalent bond. Okay. Now, we have another term called van der Waals radius. So, let's see what you mean by van der Waals radius. Van der Waals radius. Van der Waals radius is 1/2 the distance between the nuclei of two identical non-bonded isolated atoms or two adjacent identical atoms belonging to two neighboring molecules of an element in solid state. So this is the definition of van der Waals radii. And this van der Waals means it's a force that exists between the non-bonded isolated atoms or neighboring molecules, and they are very weak force of attraction. Okay, so van der Waals force means they are very weak force of attraction between two non-bonded atoms. Now, I will give an example for van der Waals radius. Suppose we have a chlorine molecule with its outer shell indicated like this, and you know that this is the bond length, which is 198 picometer. Now, another chlorine molecule along with its valence shell, this also the bond length is 198 picometer. Now, the this is the bond length 198 picometer, covalent radius will be 99 picometer. Now, what will be the van der Waals radius? Van der Waals radius you will measure from here, the one molecule, the nuclei of one molecule to the nuclei of the next molecule. Okay, so this is van der Waals radius. This, suppose this distance is 360 picometer, half of this is van der Waals radius, means this distance, which is 180 picometer. This is van der Waals radius. So you can say van der Waals radius will be 180 picometer. So actually this van der Waals radius means it implies the overall size of the atom including the valence shell. Okay, I told you this curve, this is the valence shell. So van der Waals radius means it is the radius including the valence shell of the atom, whereas covalent radius means it is equal to the radius of the core of the atom. Okay, means within the molecule we get the radius, we are not considering the valence shell when we say about the covalent radius. So which will be bigger in size? Always van der Waals radius of an element will be always greater than its covalent radius. So the first parameter, bond parameter that we have to study is bond length. Bond length is the distance between the center of nuclei of two bonded atoms in a molecule. Now, what are the factors affecting bond length? Next, factors affecting bond length. The first factor is size of the atom. Now, you know that as size increases, bond length increases. So, size increases, bond length increases. Now, you know, you take halogens, we know the halogens, fluorine, chlorine, bromine, iodine and astatine, and we know as you move down the group, size of the atom increases. So, when you consider there are hydrides, hydrides means hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide, which will be bigger in bond length, which will have the largest bond length, it will be hydrogen iodide, because iodine has the largest size. So, as size increases, bond length increases. So, tell me that order, the order will be HI, the bond length order will be HI greater than HBr greater than HCl greater than HF, hydrogen iodide greater than HBr greater than HCl greater than HF. Now, the next factor is multiplicity of the bond. Bond length depends upon multiplicity of the bond. Now, multiplicity of bond means single bond, double bond, triple bond. We know that if it's a triple bond, then the bond length decreases. That means as multiplicity of bond increases, bond length decreases. So, we can say as multiplicity increases, bond length decreases. So, always a single bond will have a larger bond length than double bond than triple bond. Now, if you check the alkenes and alkynes, bond length of carbon-carbon bonds will be in the order C single bond C greater than C double bond C greater than C triple bond C. Now, this is about bond length, the first parameter. Now, the second parameter, the second bond parameter is bond angle. Bond angle. Now, what do you mean by bond angle? It is the average angle between the lines representing the orbitals containing bonding electrons. Okay, for example, if you take water molecule HOH, the bond angle is 104.5 degree. So, it is the average angle between the lines representing the orbitals containing bonding electrons. Okay, this is bond angle. Now, the third term or the third bond parameter is bond enthalpy or bond dissociation enthalpy. Denoted by delta H. Enthalpy is H. Delta H means change in enthalpy. Dissociation enthalpy is delta H dissociation. Now, what do you mean by bond enthalpy? Bond enthalpy or bond dissociation enthalpy means the amount of energy required to break 1 mole of a bond so as to separate them into gaseous atom. For example, H2 molecule, H2 gas, when you break, it dissociates into H plus H, hydrogen atom. And delta H dissociation for this reaction is 435.8 kilojoule per mole. What do you understand from this? Delta H dissociation for this reaction is 435.8 kilojoule per mole. It means that 435.8 kilojoules of energy is required for the dissociation of H2 gas into 2 hydrogen atoms. Okay, so this is the bond dissociation enthalpy for hydrogen molecule. Now, you can see that the enthalpy unit, bond dissociation enthalpy unit is kilojoule per mole. Now, if it's a polyatomic molecule means 3 or more than 3 atoms, we take the average bond enthalpy. Okay, now this is a diatomic molecule H2. If it's a polyatomic molecule, we have to take the average bond enthalpy. Now, for example, water molecule H2O. This is a polyatomic molecule. There are 3 atoms. Now, in water molecule, you know that water molecule when it breaks like this. First, H2O will break as hydrogen gas plus OH. First, one OH bond breaks and it dissociates as H plus OH. There is a value for bond dissociation enthalpy because we had to give energy to this breaking of H2O. So, delta H dissociation is 502 kilojoule per mole. Now, next we have to break this OH bond. So, again OH bond will dissociate as O plus H. Now, some energy is needed for this breaking. That is the bond dissociation enthalpy for this is 427 kilojoule per mole. Now tell me, what is the bond enthalpy or bond dissociation enthalpy of water molecule? It will be the average bond enthalpy. Average bond enthalpy. Average bond enthalpy means it will be equal to 502 plus 427 divided by 2, which is equal to 464.5 kilojoule per mole. So, this is the bond dissociation enthalpy of water molecule. Since it's a polyatomic molecule, we have to consider the average bond dissociation enthalpy. Now, next let's see what are the factors affecting bond enthalpy. So next, factors affecting bond enthalpy. The first one is size of the atom. You know that as size increases, bond length increases, bond enthalpy decreases. So as size, first is as size increases, bond dissociation enthalpy decreases. Okay, because bond length increases. Now the second factor is multiplicity of bond. We know that it's very difficult to break a triple bond, then a double bond, then a single bond. So as the multiplicity of bond increases, bond dissociation enthalpy increases. So the second factor is as multiplicity of bond increases, delta H dissociation increases. So it's very difficult to break a triple bond, then a double bond and a single bond. Okay. Now next is number of lone pair of electrons present. So if the number of lone pair of electrons present on bonded atom increases, then what happens? There will be repulsion between the electrons. More repulsion will be there, therefore bond enthalpy decreases. So the third factor is number of lone pair of electrons. So as number of lone pair electron increases, what will happen? Repulsion increases, bond dissociation enthalpy decreases. Okay, so these are the three factors that affect bond enthalpy. Now the fourth bond parameter is bond order. Fourth one is bond order. What do you mean by bond order? Bond order means the number of bonds between two atoms in a molecule is called bond order. The number of bonds between two atoms. For example, what is the bond order of H2 molecule? How many bonds between two H2? Only one bond. So its bond order is equal to 1. Now bond order of O2 molecule. O2 we have O2 molecule is represented like this. So what is the bond order? How many bonds between two oxygen atom? 2. So bond order will be equal to 2. Now bond order of N2 nitrogen molecule. Nitrogen molecule is represented as this with a triple bond. So bond order will be equal to 3. So bond order means the number of bonds present between the atoms in a molecule. Now here you have to note something. Isoelectronic species. Isoelectronic species. What do you mean by isoelectronic species? Species which has same number of electrons. Isoelectronic species have identical bond order. For example, F2, fluorine. Fluorine, you know, it exists as F minus F. So bond order will be equal to 1. F2 and O2, 2 minus. Now what is the total number of electrons in F2? 7 into 2, 14 electrons are present in F2. Now O2, 2 minus, how many electrons? O2 has 6 into 2, 12 plus 2, 14 electrons. So since F2 has bond order 1, O2, 2 minus also will have bond order equal to 1. So isoelectronic species will have same bond order. This is one example. Same way, N2, another example is N2CO NO plus. First let's see or check whether they are isoelectronic species. N2 means 5 plus 5, 10 electron, valence electron. Carbon monoxide, we have 4 plus 6 which is equal to 10 electron. Then next NO plus means we have 5 plus 6 plus 6 plus charge, so shows that 1 electron is removed, so minus 1. 6 plus 5 is 11 minus 1 which is again equal to 10 electrons. So these three are isoelectronic species, and you know N2 exists as N triple bond N. So what is the bond order of N2 molecule? N2 bond order is equal to 3, which means the bond order of CO as well as NO is also equal to 3. Okay, so isoelectronic molecules and ions have identical bond order. These are the two examples. Now we have a question. The question is this: how do you express bond strength in terms of bond order? Okay, so how can you relate bond strength and bond order? We can say that as bond order increases, bond strength increases. Okay, or as bond order increases, the bond length decreases and bond enthalpy increases. Okay, so how can we say that? As bond order increases, bond length decreases and bond enthalpy increases. Okay, so this is the relation between bond order, bond length and bond enthalpy. Okay, so with this we complete the different bond parameters. Which are the bond parameters? Bond length, second is bond angle, third is bond dissociation enthalpy, and the last one is bond order. Thank you.